Welcome to Module 9A, Pumps, Valves, and Variable Flow. In this module, we move deeper into hydronic systems and focus on the components that determine where the water actually goes. A pump does not magically create flow through every coil. It creates head. The valves, piping, strainers, coils, and branches determine how that head is used. As BAS professionals, we need to understand pump curves, valve authority, differential pressure reset, and variable flow behavior so we can diagnose problems instead of simply increasing set points. By the end of this module, you should be able to look at a hydronic trend and ask better questions before making changes. In this module, our learning objectives are practical. First, you will learn how to read pump and system curves at a conceptual level. Second, you will apply the pump affinity laws without treating them like exact field guarantees. Third, you will understand valve CV and valve authority, because many control problems start with valves that are too large, too small, or installed in a system with poor pressure relationships. Fourth, you will evaluate differential pressure reset strategies. And finally, you will practice diagnosing variable flow problems. The goal is not to memorize formulas. The goal is to make better decisions when a building is not moving water correctly. Here is the path through the module. We start with the pump operating point, because the pump and system curves decide the real flow condition. Then we look at the affinity laws, which explain why variable speed can save energy when the system actually allows flow and pressure to reduce. Next, we talk about cavitation and suction conditions, because a pump can be enabled and still be unhealthy. After that, we move into valves, starting with CV and then valve authority. We finish with differential pressure reset, parallel pump staging, and variable flow troubleshooting. Keep one idea in mind. A variable flow system performs well only when the pump supplies the pressure that the active flow paths require. Fugal pump has a relationship between flow and head. The piping system also has a relationship between flow and resistance. The actual operating point is where those two curves intersect. This is why a pump speed command alone does not prove flow. If a control valve closes, if a strainer loads up, if a bypass opens, or if air is trapped in the system curve changes. The pump may be doing exactly what it is commanded to do, while the system still delivers the wrong flow. In the field, this means we should not diagnose from speed command alone. We need to look at differential pressure, valve positions, flow if available, pump power, and the physical condition of the system. The pump affinity laws are one of the most useful ideas in variable flow systems. For the same pump under similar conditions, flow changes roughly with speed, head changes roughly with speed squared, and power changes roughly with speed cubed. This explains why reducing pump speed can save significant energy. But we must be careful. These are estimates, not guarantees. Actual savings depend on pump efficiency, VFD losses, bypass flow, minimum flow requirements, valve behavior, and how the system curve changes. VFD does not automatically save energy. The system must actually reduce flow and pressure in a controlled way. Cavitation occurs when local fluid pressure drops low enough for vapor bubbles to form and collapse. In the field, it may sound like gravel inside the pump. You may also see vibration, reduced flow, unstable performance, or long-term impeller damage. BAS trends can help identify indirect symptoms, but the BAS is usually not enough to prove cavitation. You need field measurements and pump system knowledge. Common causes include low system pressure, dirty strainers, restricted suction piping, high fluid temperature, excessive speed, or poor pump location relative to the expansion tank connection. When you hear a noisy pump, do not simply lower alarms or force the pump harder. Investigate the suction conditions. Valve CV is a practical sizing concept. For water, CV is approximately the flow in gallons per minute that produces a one-psi pressure drop across the fully open valve. In this example, the coil needs 40 GPM and the design valve pressure drop is 4 psi. For water, the required CV is about 20. If somebody installs a valve with a CV of 80 Y, that valve may be severely oversized. The result is not just a sizing problem on paper, it becomes a control problem in the building. Small command changes can create large flow changes, the loop may hunt, and low delta T may appear. Always remember, valve selection by pipe size alone is risky. Valve authority is one of the most important concepts for stable hydronic control. It compares the valve pressure drop to the total pressure drop of the controlled branch. When authority is strong, the valve has enough influence over flow to control the process. When authority is weak, pressure changes elsewhere in the system dominate the valve. The actuator may move, the command may look correct, but the flow response is poor. BAS teams often try to fix this with PID tuning. Sometimes tuning helps, but it cannot fully correct a poorly sized valve or a bad pressure relationship. Good control starts with good hydraulics. Valve trim can be linear, equal percentage, or another characteristic. But the valve on a submittal is not the whole story. Once it is installed, the piping system changes the real behavior. This is called the installed characteristic. A valve that looks reasonable on paper can act very aggressively in the field if it is oversized or if differential pressure varies too much. This is why a 50% command does not necessarily mean 50% useful heat transfer. Before tuning a loop, check the valve type, CV, design pressure drop, actual pressure behavior, actuator stroke, and whether the coil delta T makes physical sense. Differential pressure reset is one of the most powerful strategies in a variable flow hydronic system. Instead of maintaining a high fixed set point all day, the BAS reduces pump pressure when demand is low and raises it only when the active flow paths need more pressure. But the reset must be robust. It needs minimum and maximum limits. It needs slow adjustment. It needs bad data rejection. It should not respond to one failed valve stuck at 100%. A good reset strategy protects critical loads, preserves minimum equipment flow, and reduces pressure when the system does not need it. Parallel pumps are common in larger plants. They provide capacity, redundancy, and flexibility, but staging them is not as simple as turning on the next pump whenever the system feels busy. Two pumps at low speed are not always more efficient than one pump at a higher speed. The answer depends on the pump curve, system curve, minimum speed, check valves, efficiency, and equipment limits. Good BAS logic includes lead lag rotation, minimum runtime, failure response, and stable staging. Most importantly, it should be tested across real load conditions. The goal is not just equal run hours, the goal is reliable and efficient operation. Two-way and three-way valves serve different system strategies. In a variable flow system, two-way valves reduce branch flow as they close, and the pump should respond by reducing speed or pressure. That can save energy, but equipment minimum flow must still be protected. Three-way valves maintain flow by mixing or bypassing. That may be appropriate in some constant flow systems, but it can also create bypass flow and raise return temperature. In low delta T problems, three-way bypasses are often part of the story. Never change a valve type without reviewing the plant, the pump strategy, the minimum flow path, and the effect on return temperature. Here is a realistic field scenario. A facility installs VFDs on secondary pumps and expects major savings. But after installation, the pumps stay near full speed. The first reaction may be to blame the drive programming, but investigation finds that the remote differential pressure set point was based on an assumed design value, and the sensor was effectively looking at a branch with a manual balancing valve nearly closed. The pump was not responding to true system demand. It was responding to a distorted pressure condition. The lasting fix is to correct the branch, verify sensor location, and then commission the pressure reset. The VFD enables savings, but the system strategy creates them. Let's pause on common mistakes. Do not assume pump speed equals flow. Do not ignore suction conditions. Do not select valves from pipe size alone. Do not use PID tuning to hide poor valve authority. Do not let one bad valve reset the whole distribution system to maximum pressure. And do not claim VFD savings without a baseline and final measured power. A good field checklist protects you from these errors. Confirm pump curves, speed limits, valve CV, valve authority, sensor location, and trends for power, flow, and delta T. A professional BAS response begins with evidence. Before we close, answer these questions. If a pump is near full speed but remote differential pressure is low, do not simply raise the set point. Check the sensor, tubing, valve positions, strainers, air, and system resistance. If a valve is oversized, expect poor control and possible low delta T. If a reset strategy uses the most open valve, one failed valve can force the whole system to maximum pressure. And finally, a VFD project is not proven by the presence of a drive. It is proven by measured power reduction under comparable operating conditions. Your assignment is to apply this module to a real or sample hydronic distribution system. Identify the pump and VFD limits. Record where the differential pressure sensor is installed and decide what it actually represents. Review selected control valves for CV, authority, and command behavior. Then propose a safe differential pressure reset improvement with minimum and maximum limits, bad data rejection, and validation criteria. The main takeaway is simple. Variable flow optimization is not just a programming exercise. It is a physical system, measurement, valve, pump, and controls exercise. In the next module, we move into refrigeration, chillers, and heat pumps.